Okay, let's start with a brief review of some of the vocabulary here. First thing is ratio, and a ratio is a comparison of two things. For example, I might have M&Ms and I'm comparing how many are red in my pile to how many are blue. And if when I looked at it and simplified this ratio, I saw that for every 3 red, there were 4 blue, I could write the ratio this way, or I could write it as a fraction this way, red to blue. I want to make sure that I keep it matched up with this, my indicator here of what's being compared. If I switch it around this way, now I'm comparing it the other way around, blue to red. So you should always make sure that you've got some kind of a label indicating what your ratio is comparing. A scale is a special kind of ratio that we use to compare lengths. For example, if you are going to make a model car to represent a real car, you might have a scale, and that scale might say for every 1 unit on your model, it represents a distance of 50 units on the actual car. So every 1 inch on the model would represent 50 inches in the actual car. Every 1 foot on the model would represent 1 foot on the actual car. When there's no labels indicated on your scale, it says no matter what unit of measure you're using, the other item is using that same unit of measure. On maps, you'll oftentimes see something like this that says 1 inch is going to equal 200 miles. And then they are indicating the units of measure, and therefore that clears up that idea of what are my units that I'm supposed to be using. A proportion is just an equivalence between two ratios. So coming back up to this example here with the M&Ms, if I know the ratio of red to blue in a bag of M&Ms is 3 to 4, meaning every 3 red M&Ms I should find 4 blue ones to go with them, and I count up and realize that I have 100 blue M&Ms, I could figure out how many red ones I should expect out of my supply by knowing that these two fractions will be equal, or these two ratios. So since the denominator of this fraction here is 25 times larger, the numerator must also be 25 times larger. So that tells me that I would have 75 red M&Ms in this pile. Some of you like to solve proportions using cross multiplying, and you can do that if there's an equivalent statement between them. You know that what you get multiplying this way through the equals, 3 times 100 or 300, is going to be equal to what you get multiplying this way through the equals, or 4 times x. When you then solve for x, dividing by 4, you'll find that x has to be 75, the same thing we found the other way. Now, another kind of ratio that we use other than a scale is a rate, and you see rates all the time. We talk about miles per hour that we're going to drive, or we might talk about ounces per day of water that you're supposed to drink, or you might talk about beats per minute of a heart, or any number of other things. When we're comparing things with different units, different actual items being compared, then it's called a rate, but it still is just a ratio. So let's look at some examples here. We have a human heart, and the scale model is 16 feet long. Now, obviously, this is larger than the actual heart. So when I look at this scale, I know that the larger number must be my model, and the smaller number must be my actual heart. So for every 1 centimeter on my actual heart, I'm going to make it 32 centimeters on this model. So I can write myself a proportion to help me figure out the missing piece of information here. How many inches long is the actual heart? So since my scale is 32 to 1, and I'll want to have my labels out here, this is the model compared to the actual. Then I can come over here, and I know that since the model is 16 feet long and the model is on top, I'm going to put 16 here, and the thing I don't know, the actual length, is going to be right there. I can look at this and pretty easily see that the numerator was simply divided by 2, so I know the denominator will also be divided by 2, and I will get 1/2. Because the units have to be the same, and this was feet, This 1/2 is a number of feet. The question asked me, though, how many inches long it would be. So you need to realize that 1/2 of a foot is 6 inches. And so the actual heart would be 6 inches long. So hopefully you feel like you understand scale a little bit better. When you're trying to use that scale to determine an actual distance, we set up a proportion, and it's extremely important that you have your label set up so that you put that 16 feet in the right place. We wouldn't want to put it on the bottom or you end up with a very large heart. So let's go on and look at rates now. There's often times where the rate that you're given is not the units that you want to use. For example, right here it says that Selena is running at 10 kilometers per hour, but we want to know how many kilometers she will cover per minute. And so we're going to change what was a rate in kilometers for every 1 hour. We want to change this into a number of kilometers per every 1 minute. And the way we do this is by multiplying by conversion fractions. These conversion fractions are simply something that you create so that the top and the bottom of the fraction have the same value, and the fraction is actually equal to 1. But we're using different labels. So since I want to get rid of the number of hours and change it into minutes, I want to put the number of hours on top, because whenever I divide something by itself, I get 1. So I want to get rid of hours, I want to end up with minutes, and I need to make sure this fraction is equal to 1. Well, I know that every 1 hour is the same as 60 minutes. So if my fraction has 1 hour on top and 60 minutes on bottom, the top and the bottom of the fraction are equal to each other. My hours will cancel out because I'm dividing by itself, and I'm left with 10 divided by 60, or 1/6 of a kilometer per minute. Now, my instructions did tell me to round to the nearest hundredth. So when I divide this, I get 0.1666 repeating. And so rounding to the nearest hundredth, which is this place, gives me approximately 0.17 kilometers per minute, or in other words, 17 hundredths of a kilometer per minute. That would be her speed in kilometers per minute. Let's look at another example. We've got a cheetah here who's running 60 miles per hour, and we want to figure out how many feet he covers in a second. So we're changing this rate to feet per second. So there's a couple things we need to know here. I need to get from miles to feet. So I need to know how many miles are equal to how many feet, and that's 5,280 feet for every 1 mile. And then I also need to go from hours to seconds. Now, you might not know right away from hours to seconds, but you should know that 1 hour is 60 minutes, and every 1 minute is 60 seconds. So I can combine these into one and say that in 1 hour, I will have 60 sets of 60 seconds, or in other words, 3,600 seconds. Now I can go ahead and solve this problem using these conversion fractions. So the first thing I'm going to do is rewrite my rate here, and my rate that I was given was 60 miles per hour. So I'm going to write 60 miles per 1 hour. And let's take care of our miles first. So since miles were on top, I need to make sure that I put my 1 mile on bottom. And my 1 mile was equal to 5,280 feet. So I'm going to write the 5,280 feet up here on the top. My miles will cancel off miles. Miles divided by miles is just 1. And it's going to leave me with feet on the top. Now the next thing I need to do is get rid of my hours. And since hours were on the bottom, I want to make sure in this conversion fraction that I have hours on the top so that they can cancel off. And I know from here that every 1 hour is going to equal 3,600 seconds. So now my hours divided by hours will give me 1 there as well. So what I'm left with now on the top is 60 times 5,280, and the only units left up there are feet. In the denominator, I have 1 times 1 times 3,600, and the only label left there is seconds. So by pulling out a calculator, I can do the multiplications, and I can divide this and find my speed in feet per second. So when I used my calculator and I multiplied in the top, I got 316,800 feet for every 3,600 seconds, and dividing that out gets me exactly 88 feet per second. So my cheetah, who's going 60 miles per hour, is actually covering 88 feet every 1 second. That's impressive. All right, another example here of rates. When we look at this, we've got this fastest car, and this fastest car, it says traveled at 413 kilometers per hour as its max speed. And then we've got here a more futuristic looking car. It is the Thrust, and it's actually like a jet vehicle here. And it traveled up to 771 miles per hour. So I'd like to compare these two and see just how much faster the one is than the other. In order to do that, since this is in miles per hour and my other vehicle was in kilometers per hour, I'm going to change this one into miles per hour since it's what we're more familiar with. And even though I could look on the internet for a conversion ratio, we actually have a really slick tool right here in our car that we look at every day. When you look at your speedometer, you should see 2 spots on there where you can pretty easily tell an equivalence between miles and kilometers. There's this one right here where the 50 and the 80 just about perfectly line up. And then there's the one here where the 160 and the 100 almost perfectly line up as well. So this says that if I'm going 100 miles per hour, that's the same as going 160 kilometers per hour. Remembering that per hour just means in each hour, that means that 100 miles is the same as 160 kilometers, approximately. So if I want to convert my 413 kilometers per hour into miles per hour, just like we did before, I'm going to take the 413 kilometers per 1 hour, and I'm going to multiply by a conversion fraction. I want kilometers on the bottom to cancel out the top, and I want to end up with miles, and now I'm going to use this equivalence here. So I have 160 kilometers is the same as 100 miles. When I multiply through, I get 413,000, so 41,300. My kilometers have canceled out, leaving me with just miles up here. And in the denominator, I have 160, and the only label left is hours. So if I divide this one out now on my calculator, I'm going to get the answer up approximately 258 miles per hour. So when we're looking at these distances or these speeds, and it said 413, it looked like, if you weren't paying attention to units, like it was going a little bit more than half the speed of this one. But when we actually figure out what it really is, we find out that it's only going about a third of the speed of that jet car that we saw on the other page. All right, so one last thing to look at is proportions, and while we've already looked at some like this that are fairly simple to solve, we will go a little bit further with it. Let's start here. Again, thinking about equivalent fractions, I can use the idea that I know that 2 times 4 gives me 8. So in my numerator, I must multiply also by 4, and negative 5 times 4 is negative 20, so I know that y would have to be negative 20. If I use the cross-multiplying process, which says the products across the equals should be the same, negative 5 times 8 should be equal to 2 times y, I can divide both sides by 2 and determine that y has to be equal to negative 20, which is exactly what we got using the idea of equivalent fractions. Now this other fraction isn't quite as easy to do that with because I can't look at 3 and figure out what to multiply it by to get me 5, so I might be more inclined to use cross-multiplying. But remembering that division is just the reverse of multiplying, I can figure out what to multiply by if I take the result 5 and divide it by 3. In other words, 5/3. If I multiply 3 with 5/3, I'll get 5. So coming down here, I can multiply 9 with 5/3, and it should tell me what m is. Notice when I'm multiplying a whole number by a fraction, I put the whole number over 1. I can multiply straight across and get 45 over 3, and then simplify down to 15. Or I could have simplified right away because I know that 3 divides into both a top number and a bottom number, leaving me directly with 15 over 1. Notice if I had chosen to do the cross multiplying, I would take 3 times m, cross multiplying through the equals. The cross products are equal, equals 9 times 5, and that's 45. And then I'm going to divide both sides by 3, and just like you saw in our method here, we're going to get 15 as the value of m. Now, proportions like this one here are a little bit more complex because instead of just having a g up here, now we have a g plus 3. And you might wonder why we would ever run into a scenario like that. So let me give you an example. In this situation, obviously somewhat made up, we have a card business that you're running, and you have your total amount that you made in 1 month, but you did not keep track of how many cards you sold. The next month, you know that you sold 30 cards more than last month. You had all your regular customers bought the same amount they always do, but then you ended up selling 30 extra cards. And your total income that month was $217.50. Now, since your price per card was the same each month, we should be able to figure out how many cards you sold. So setting up a ratio here of price per card means I'm going to take the total money, $105, and divide by the number of cards, which I don't know. For the first month, that ratio gives me my price per card. For the second month, where I sold $217.50 worth, but I know that I sold 30 cards more than last month, my ratio would look like this, x plus 30, to get that new total. So when I multiply or do my cross products, I need to make sure that I remember that this 105 here is getting multiplied by a number 30 larger than x. I have to make sure that when I multiply the 105, it's not just getting multiplied by x or just getting multiplied by 30. It's getting multiplied by the total of x plus 30. So I'm going to use some distributing there when I do that multiplication. I'm going to get 105x plus, and here I'll get 3,150. And this equals 217.50x. Now, because I'm solving an equation, I want to always remember to look back at this and say, where are my x's? I have x's on both sides. I need to get them together. Since my constants are only over here, I will get my x's together on the other side by removing them from this side. So this is 0 x's now, leaves me with my 3150. And on the other side, I'll be left with, let's see here, 112.50 times x. Now, last step in solving is always to figure out what 1x equals. So I'm going to have to divide by whatever the coefficient is. In this case, 112.50. So I'm dividing both sides by 112.50. And when I pull out my calculator to do that division, I get exactly 28. Now remember, X stood for a number of cards that I sold in the first month. I'm being asked how many cards I sold each month. So in the first month, I know that I sold 28 cards, which means in the second month, I sold 30 more, which was 58 cards. So even in these scenarios where you don't have context around it, the idea remains the same. This numerator as a whole is going to be multiplied by 4. So I need to make sure that I put parentheses around the g plus 3 to ensure that it gets distributed. The other way, I just have 5 times 7. So 4g plus 12 equals 35. Now again, I'm solving this equation, so I want to identify where are my variables, only on the left. Where are my constants? They should only be on the right. So I'm going to subtract 12 from each side to get rid of the 12 that are here. So now I get that 4g equals 23. And if I divide now by 4, I can find that g must equal 5.75. or 5 3/4. Now, even though it's going in a fraction, that's okay, because this might represent the cost of a card, or it might represent how many of something you bought, an amount of weight. And so we could end up with a ratio like this, having a decimal or a fraction as one of those two values. Coming over to this one, same idea. I'm going to multiply across, making sure that the 2 gets multiplied by the entire denominator of y minus 3, and going the other way, that I get 6 times 7. So I have 2y minus 6 equals 42. And then again, solving, my variables only on the left, so I want to get my constants only on the right. Gets me 2y equals 48, and dividing both sides by 2 gets me a y value of 24. Make sure you're going back and checking your answers. If you put 24 in for y, you would have 6 over 21 equal to 2 over 7. If you divide 6 by 21, just to check a quick way, 6 divided by 21 is approximately 0.2857. 2 divided by 7 gets me the exact same decimal. So since I'm getting the exact same decimal for each side of this fraction in my check, that's how I know that my answer worked out all right. So hopefully this gives you a much better feel for how to do the problems that you're required to have done for Monday. If you're still struggling, remember this comes from Chapter 2, Section 6 in our Holt Algebra book, and you can go to my.hrw.com and use your login information to watch more videos where Professor Edward Berger or his counterpart can help explain this a different way for you. Good luck.